This is section 3.2, polynomial functions. This first slide right here, along with the second slide, just gives some real-world examples of some polynomial functions. We see in this first one a roller coaster, and then in the second one, if you've ever played Angry Birds, right? So we'll talk about how to identify a polynomial function, and then you can come back and see how this would apply. So just in general, when we talk about polynomial functions, if we look at the integers cannot be negative and there cannot be fractions in the integers. So notice on the left side of the screen, I'm sorry, I think I said integers, exponents, all the exponents, right, are positive integers. And then on the right side, we see examples of what would not be considered a polynomial. And if you look, our exponents are fractions. We have a negative value there, and then even 0.5, right? That would be equivalent to 1/2. So what we're looking for are positive integers to identify a polynomial function. And then when we talk about the degree of a polynomial function, we're talking about the largest exponent. And this also states how many solutions there are to this polynomial. So notice here, we're actually missing an x here. So in this function, negative 2x squared minus 3x plus 2, that is a polynomial, and I know that because I don't have any fractions, nor do I have any negative values up in my exponents. And then when I look for the degree of that polynomial, it would be 2, because that is the largest exponent. Okay, I just wrote in that 1 just so we can identify that. Although we don't see an exponent there, we understand it to be 1. Now, my degree is 2, and also there are 2 solutions. And we'll talk about that a little bit more. We can say solutions, zeros, x-intercepts, but that degree will also give us the amount of solutions. Okay, if we look to the one on the right, we see that our exponents are 5, 4, 3, 2, and 1. Okay, there's no fractions there, there's no negative values, and so we do know that this is a polynomial function. And then the largest exponent would be our degree. So this polynomial has a degree of 5, and that also tells us how many solutions. So we have 1, 2, 3, 4, and then this fifth one would be right here where it slightly goes off the screen. So another way that we can identify a polynomial is how the graph is, right? So if the polynomial function has a degree of 2 or higher, then you'll see something like what's on the left side of the screen, where we have these smooth continuous lines, right? And so there's no jagged edges or any sharp corners there. We see very nice rounded curves, right? Right there and there, here, here, and here. And then they're continuous, meaning that it doesn't break apart like we've seen in like piecewise functions. So you just have these nice, smooth, continuous graphs. Where on the right side, you see this one breaks apart. So there's a discontinuation here. And then these sharp corners, right, would give me a sign that, okay, those are not polynomial functions. So that's just one way to identify it, looking at the graph. But remember, we can also actually look at the mathematical equation, the actual polynomial function written out as f of x equals, and then say, okay, let me look at my exponents. Are any of my exponents negative? Are any of them a fraction? So one thing that we talk about in polynomials is their end behavior. And basically we're saying, look, the ends of this polynomial function, what is it doing? basically. And so that name is not very creative, right? End behavior is how the ends are behaving. And in this case, we see that it rises left and rises right. So those are only going to be our options. Either we'll describe the left tail as rising or falling, and then we'll describe the right tail as rising or falling. And we can have all different combinations of that, and we'll talk a little bit about what that looks like in the polynomial, but those are the only options, rising or falling, and then we just simply describe the left tail and the right tail. Okay, so on this next one, only looking at the ends, so only looking at my tails, left tail is falling to the left, so falls left, and then rises to the right. And it's literally just that simple, where I'm just saying, okay, what's happening at each of my ends? Okay, so we have an answer here, but let's talk about how we would even get to that answer filled in. All right, so the polynomial function is f of x equals negative x raised up to the fourth power plus x squared. Okay, so let's first just talk a little bit about what we discussed about knowing that it's a polynomial. So they're telling me that it's a polynomial function, but just to confirm that, I look at my exponents and I do not have any negative exponents, nor do I have any fractions in there. If they ask me what the degree of this polynomial function would be, it would be a degree of 4, because that is my largest exponent. Okay, now when I'm determining how this looks, I can absolutely graph this, but let's talk a little bit about what to look for in the actual function to help us determine what's happening with the end behavior. So when I look at the degree, so the largest exponent, if it is even, then both of my tails will have the same behavior. Okay, not even taking into consideration whether they're rising or falling. That's always the first thing that I personally identify. I say, okay, let me look at my degree. It's a 4, it's even. So that means both of my tails are either rising or both of them are falling. But when it's even, then they're doing the same thing. If it's odd, then they're doing different things. One will be rising and one will be falling. In this case, with 4 being an even number, that means they're both going to be doing the same thing. Then once I determine that, I look at the coefficient of this leading term. It would be -1, right? It's understood when we just had that negative there that it's a -1. And that will tell me what they're both doing, because they're both doing the same thing. So one thing I like to say is it tells me how my story ends. Is it going to end negatively? Then that means that my right tail is going to be falling. Since we already determined that both of them would be doing the same thing, then that means that my left tail will be falling as well. So to sort of recap that, because that's a lot of information, the very first thing I'll look at is the degree of my polynomial. If my degree is even, and it says this at the bottom of the slide, if it's even, then both are doing the same thing. And I think if they're odd, that other one's acting odd, right? But if it's even, it's like, okay, you're meeting me where I'm at. We're even, we're on the same page. We're both falling or we're both rising. After I determine whether they're doing the same or the different or going different directions, then I look at my coefficient, and that will tell me how my graph ends. I say how the story ends. So it's negative, so it's going to be falling, and that's why we see if it's negative, they'll both be falling. If it's positive, then they both would be up. Okay, and remember, they were both doing the same thing because if we have an even power, then they do the same thing. Okay, so looking at this, immediately when I said, oh, there's an even power of this polynomial, then I could cross out B and D because the ends are acting different, right? One's falling, one's rising. Then I said, okay, it'll either be A or C because both the tails are doing the same thing. But then that negative coefficient, -1, tells me that they're both falling. So that knocked out A, leaving us with C. Hopefully that makes a little bit of sense. I feel like it's a little bit more challenging to explain it rather than show it in person because I usually do like goalpost arms to show, okay, both my tails are going up, or like upside down goalpost arms to say both tails are going down. And then I don't even know how to describe it, what kind of arms, but almost like disco arms. So one arm going up and one arm going down to describe when our tails are different. So let's look at the next one. Okay, so, oops, we got some answers on this one too. That's okay. So looking at the leading coefficient, right, we can say, all right, this is an odd exponent because that's the leading coefficient, and what determines that is that it's has the greatest exponent. So my leading coefficient gives me that 7 as an exponent, which is odd. So that tells me different tails. Well, that's supposed to say different tails. So one's going up and one's going down, okay? Now I look at the coefficient. It's a +3. I always say this tells me the coefficient tells me how my story ends. So because it's a +3, it means it's going to end positively. So I'm looking at something like this. Okay. If it would have been a negative number, then it would have looked like this with the last tail ending. Okay. So falls left, rises right. And I would actually just maybe scratch something like that on your paper because actually drawing it out and then actually saying falls this way, rises this way can be a little bit confusing. All right, so let's go ahead and graph this, and notice that we're only going to graph that leading coefficient because it does not matter what the rest of the polynomial is doing. It doesn't matter if it was plus 8x to the 5th plus 3000x to the 4th. It does not matter because the only thing we're worried about are the ends because it's asking us for end behavior. So let me go ahead and open the calculator. Okay, excuse my itty bitty calculator. I'm not sure what's going on with it and why I can't get it to a regular size. But hopefully you can see this. So we'll press 5 to get into graphing. And then I'm going to say 3x to the 7th power. Execute it. F6 to draw it out. And boom. Falls to the left, rises to the right. So you very much can do that instead of, going through the reasoning of it. But it's very important to understand the reasoning of it still so that you can check it. Because what if I accidentally put -3, or it was supposed to be -3, and then I accidentally put +3. So just to sort of confirm it with your calculator, getting that down would be a good idea. All right, let's see what we got next. Okay, so they want us to graph the following and find the x-intercepts. It's showing this on here, but let's go ahead and still do it and see how we got there. X squared plus 8x plus 15 So if we were to factor that, we would come out with x plus 5 and times x plus 3 as its factors. We'd set each of those equal to 0, and I would get negative 5 and negative 3, right? This is going to be a much quicker way to do as we graph it. Same thing over here with g of x equals x cubed minus 10x squared plus 25x. Notice the factoring there. We factored out x, and then we went ahead and factored it to x minus 5 squared. So if I set each of those equal to 0, I would get x equals 0, and then also x equals 5. Notice that here on the left, x plus 5 and x plus 3, when I set each of those equal to 0, I got x equals 5, negative 5 one time, and I got x equals negative 3 one time. And the graph passes through during those, or at those points, right? Over here on my g of x polynomial, it shows me that I get x equals 0 once, but I get x equals positive 5 twice. So notice that at the x equals 0 once, my graph passes through the x-axis. But where I got x equals 5, it touched and turned. The connection there is if you have a solution that occurs an odd amount of times, such as 1, it will pass through the graph. But if it has a solution that we'll call, we're going to talk about the term multiplicity. So how many times does it happen? An even multiplicity, it happens twice in this case, so it's even, it will touch and turn. So let's go ahead and graph it. X squared plus 8x plus 15. Draw it out. And you see it passes through negative 5 and negative 3. Never trust your eyes, okay? Yes, it looks like negative 5 and negative 3, but always confirm it. So we're going to go to GSolve, F5, and then you're going to press root. Remember in one of the earlier slides I said we have different names for solutions. So we can refer to them as solutions. We could refer to them as zeros. We can refer to them as x-intercepts and or roots. So that's what we're looking for on the calculator here. So after we press GSolve F5, then we press F1, and boom, it takes us to our x-intercept, our solution, or 0, whatever you refer to it as. So notice it says x equals negative 5. You can arrow over, and it'll give you x equals negative 3. So always confirm it, because your eyes might tell you, oh yeah, that's negative 5, and it might be negative 4.9999. So it's just nice to confirm it. Another way to confirm it is we can actually go out to the menu and go to the table. And okay, so we're going to have to edit our table because I'm looking for negative 5 and negative 3, and notice it starts at 1. So let's go back out here. Let's press set, F5. We're going to start at negative 6. We wouldn't have to. We could have started at negative 5. And then it's okay if it ends there. We won't go that far. Real quick, in set, this is where your table starts, ends, and then this is the units that it travels by. Okay, so look, now it's starting at negative 6, negative 5, 0, negative 3, 0. So that confirms it again that yes, indeed, those are my x-intercepts. Okay, I'm actually going to write this in. Be careful when you're working in my math labs. Just a lot of times it'll ask you to just list the x-intercepts, but if it asks you for an ordered pair, make sure that you put -5, 0 in those parentheses as an ordered pair, and then -3, 0. So just be careful of how they ask it, because it's very frustrating when you knew what you were doing, you knew what you were talking about, and then they count it wrong. All right, let's go ahead and put in this g of x function. So it's x cubed minus 10x squared plus 25x oh, we're in the table. So first let's go to the graph. That's the good thing, is once you put it into the table, it'll be in the graph, or vice versa. All right, so it looks like it's passing through 0, and then it looks like it touches and turns at 5. Again, I can do the factoring right. I can graph it and press G solve root. Boom. 0, arrow over, 5. So notice that the degree of my polynomial 3 told me how many solutions I have, right? That can be confusing if you don't understand that, oh, at 5, it counts as 2 of them because it touches and turns. You can say, well, hold on, that can't be true. I have to have another root because I saw 0 was one and 5 was the other. But because it touched and turned, it accounts for 2 of them in this situation. Okay, we can also confirm that with the table too. So x equals 0 and also positive 5. Let's see what we have. Okay, so we can just start off by graphing this, but let's go ahead and do the math of it too. So I'm going to factor out an x. I get x squared minus 12x plus 36. I continue to factor, and I get x minus 6 times x minus 6. Okay, if I set each of these equal to 0, I would get x equals 0, x equals 6, and x equals 6. Let's go ahead. So what I'm thinking is that x equals 0, and 6, it will cross through the x-axis here because it occurred once. Like I said, we call it a multiplicity. What's the multiplicity of that 0? Well, it occurred once. I got that answer once, so it will cross through there because 1 is an odd number. But here, we got x equals 6 twice, so this will touch and turn because the multiplicity is even. It had a multiplicity of 2. It occurred twice. All right, so let's see if this is true. Again, if you're like, I don't even know where to start with that, thank goodness for the calculator. Like I said, it's very important for you to understand what your calculator is doing, but thank goodness that if you get a little bit lost, you can punch in your calculator and then sort of navigate around. Okay, so x cubed minus 12x squared plus 36x. Okay, draw it out. I'm gonna move a little bit this way. All right, so it does look like it passes through 0 and touches and turns at 6, but let me confirm. I'm gonna do G solve root, boom, x equals 0 and x equals 6. So we did indeed confirm that. Good, hopefully it's making a little bit more sense. Practice makes perfect, so get in the homework. So let's look here. We did find that the zeros or the solutions, the roots, the x-intercepts, right? All of those names mean the same thing. Were 0 and 6. The multiplicity of the leftmost zero. So this is the way my math lab will ask you the question. It'll say, what was the multiplicity of the leftmost zero? So on my graph, let me pull that back up. To the far left, it was 0, right? So what was the multiplicity? All they're asking you there is how many times did it occur? It occurred 1 time, okay? Because that is an odd number, it crosses the x-axis. And then the multiplicity of the rightmost zero, so when we go over to the right, it's 6. The multiplicity is how many times did we get that solution? Well, we got it twice, right? So it touches and turns away at the x-axis, which we do see that there. I'm trying to think of a corny rhyme that I made up in class. I think my students helped me too, to help remember this. I'm just one of those people where if you give me rules to remember, they just all get jumbled up. But if you give me something corny and silly to remember, it sticks in my mind. And so for those students that are like that, sometimes this is helpful. I think for this first one, we said, Odd Todd kept going on through. It was something with like odd, the odd number. Odd Todd didn't make 2, therefore he just kept on going on through. Something like that. So if the number is odd, we know that it's just going to keep going on through the x-axis. And then Even Steven came to town, but then he decided to turn around. So if the number is even, it will touch the x-axis, which is in the silly rhyme, town, and then turn around. So Odd Todd didn't make 2, so he just kept on going through. And then Even Steven came to town, but then he decided to turn around. If you're like, that absolutely is ridiculous and it's not going to help me, that's fine. Let it go. But if it will help you, or maybe make up your own, but sometimes things like that will help us remember.